Hello there, and welcome to this live session of the Chemistry Clinic brought to you by Boost Revision. I'm Dr. Owisi. In today's session, we're going to be looking at equilibria and in the context of Kc calculations and Kp calculations. Essentially, we're following up on Thursday's session where you were introduced to the idea of chemical equilibria and what the equilibrium or equilibria tells us about a chemical reaction. You looked at factors affecting the position of the equilibrium and also the characteristics defining chemical equilibria. In today's session, we're going to be looking at calculations of equilibrium quantities, in other words, the number of moles of reactants and products at equilibrium. And then we're going to be using the total volume or the total pressure of your reaction system to determine what the value of Kc or Kp is. As usual, we will be looking at some actual exam questions involving Kc and Kp calculations. I've also got a set of practice questions looking at calculating equilibrium quantities that I will work through with you. If there are any questions at all, do use the chat box, drop me a line and I will be quick to answer your questions for you. I will, as usual, be sharing the screen of my iPad with you, and if you just give me a few seconds, I will do that and then we will be ready to start the session. Okay, so it looks like we're all set to go, and so we're looking at equilibria and calculating Kc and Kp, and so this is a follow up to your session on Thursday, which looked at what equilibrium is, and we looked at the Le Chatelier's principle and the various factors affecting the position of equilibrium. So just a quick recap, you've got a generic equation shown on the screen where you've got A and B reacting and in the process forming C and D. And of course, in a closed system, this reaction will reach equilibrium, and we can write an expression that describes the position of equilibrium. And so the expression for Kc in this generic equation should be given by the concentration of C raised to the power lowercase c. In other words, lowercase c is the number of moles of C in the balanced equation, and that is multiplied by the concentration of D raised to the power lowercase d, and the bottom term will be the concentration of A raised to the power lowercase a multiplied by the concentration of B raised to the lowercase b. Okay, so that's your expression for Kc. And just to remind ourselves what this expression tells us, well, it tells us about the position of the equilibrium. So it gives us a ratio of reactants to products. So ratio of reactants to products. Or perhaps more accurately, products to reactants, seeing as we've got the products as the numerator. And this tells us where the position of equilibrium lies. Okay, so if you've got the equilibrium very much towards the product side, in other words, there is a lot more products present at equilibrium than there are reactants, then you would expect a Kc value that is greater than 1. Okay, so where Kc is greater than 1, you've got more you've got more products than you've got reactants. Okay, and conversely, if Kc is less than 1, it means that you've got more reactants present at equilibrium than you've got products. Okay, so it's very important to note the magnitude of your value of Kc, because it's telling you where the equilibrium lies at, for a particular reaction. Okay, so let's look at how to calculate Kc, Kp, and units. Okay, so for reactions in the gas phase, instead of using Kc, we're going to be using Kp. We're going to be talking about Kp. Now, Kp is used because when you're looking at reactions in the gas phase, it is more appropriate to think of the concentrations of those gases in terms of the pressure of those gases. So in terms of the pressure exerted by each of those gases in your closed system. And the pressure exerted by each of those gases in your mixture of gases is known as the partial pressure. Okay, so we'll look at how to calculate the partial pressure for each gas at equilibrium, and then how to use these partial pressure values to work out the value for Kp. Now, the reason we think in terms of pressure for gases is because all gases are miscible with each other. So it's a bit incongruous to think of one gas being dissolved in sort of another gas which is considered a solvent. Well, you could think of it sort of in the opposite terms. So because both gases or all the gases present are miscible in each other, you can't really think in terms of sort of concentration and sort of solute being dissolved in solvent. So we're thinking in terms of partial pressures. Okay, so if we're writing an expression for Kp for this reaction in the gas phase, where you've got A reacting with B to give you C and D, very similar to what we did with our with Kc, we're going to use a small case or lowercase p to indicate partial pressure, and we're going to use normal brackets rather than square brackets. Square brackets, remember, refer to concentration. The normal brackets refer to partial pressure. So we're looking at the partial pressure of C, which of course is a gas, raised to the power lowercase c, multiply that by the partial pressure of D, again, gaseous D, raised to the power lowercase d, divided by the partial pressure of A, raised to the power lowercase a, times the partial pressure of B, raised to the power lowercase b. Okay, so not too dissimilar to how you would write an expression for Kc, except with gases, you want to write an expression in terms of partial pressures. Okay, so partial pressure, which I've highlighted here in yellow, and that's what these values are. Okay, so we're talking about the partial pressure of C raised to the power C, lowercase c, so the number of moles of C in the balance equation. Partial pressure of D raised to the power D, which is the number of moles of D in the balance equation. So these are the partial pressure terms. Okay, so that's an expression for the equilibrium constant Kp. Now, how do we calculate the partial pressure? Okay, so to calculate the partial pressure, you need to know what the total pressure of your system is. And this is typically given to you in order to allow you to calculate the partial pressure. So to calculate the partial pressure, we need to know what the total pressure is. And we need to know what the mole fraction is for the particular gas you're working out the partial pressure for. Okay, so total pressure times the mole fraction. Okay, now you may then want to know what the mole fraction is. Let's highlight the mole fraction here. Okay, so the mole fraction is given as the number of moles of a gas divided by the total number of moles of gases at equilibrium. Okay, so to work out Kp, we need to know what the partial pressures of the different gases in the mixture are. To work out what the partial pressure is, we need to know what the total pressure is, and we need to know what the mole fraction is for each of those gases. And to work out the mole fraction of each of those gases, we need to know the equilibrium number of moles of a particular gas and divide that by the sum of all of the moles of gases present, so the total number of moles of gases present. Okay, so let's put this into practice then. So calculating equilibrium quantities is something that is very important as far as getting these calculations right. So to calculate the equilibrium concentrations or equilibrium partial pressures, we need to know the equilibrium number of moles of each of the substances in the reaction. In other words, at equilibrium, we need to know how many moles of reactants, each of the reactants there is, how many moles of each of the products there is. Okay, so let's look at the examples shown on the screen. You've got nitrogen reacting with oxygen to give you nitrogen dioxide. All of these reactants are in the gaseous phase, so you can imagine having to work out Kp in terms of partial pressures. But before you can do that, you need to know how many moles there are of each of those substances at equilibrium, and you would also need to know the total pressure so that you can work out what the partial pressures are. The first thing we need to know is how many moles there are of each of these substances at equilibrium. Now, in the table I've got underneath the equation, we've got information about how many moles there are of the different substances at the start of the reaction. So this is before we've reached equilibrium. So the initial moles is referring to information we've got before equilibrium is reached. So if we highlight this, so initial moles, and perhaps annotate that, this is before equilibrium is reached. Okay, so that's what we've got at the start. We've got 1 mole of nitrogen gas. We've got 4 moles of oxygen gas, so oxygen is clearly in excess here. And we've got 0 moles of nitrogen dioxide. So our starting conditions are 1 mole of nitrogen, 4 moles of oxygen, and no nitrogen dioxide. Now, if we leave this mixture for a period of time, we're going to reach equilibrium. Okay, so at equilibrium, you're going to have a certain number of moles of each of your reactants and your product. Okay, so equilibrium moles is what we need to calculate. Now, to start us off, we've been told that there is 0.5 moles of nitrogen at equilibrium. Okay, so we started off with 1 mole of nitrogen at the start. At equilibrium, we've got 0.5 moles of nitrogen. So the first thing we want to do is work out, therefore, how much nitrogen has been used. Okay, so we can very quickly show this, and say that we've used up 0.5. Okay, so minus 0.5 to give us that equilibrium number of moles, right? So 1 mole of nitrogen at the start, 0.5 moles of nitrogen at equilibrium, or at the end if you want to. That means that you've used up 0.5 moles of nitrogen. Okay, so armed with that information, we can work out how many moles of oxygen we should have at equilibrium. How do we do that? Well, to do that, something you've been doing for a while now, paying attention to the molar ratio of reactants and products in a balanced equation. So if we look at nitrogen to oxygen, we've got 1 mole of nitrogen to, let's undo that, let's use a different color to make it stand out a bit more. Let's use yellow. So we've got 1 mole of nitrogen, N2, reacting with 2 moles of oxygen. Okay, so the ratio of nitrogen to oxygen is 1 to 2. That means that if 1 mole of nitrogen reacts, it will need 2 moles of oxygen. So we know that only 0.5 moles of nitrogen has reacted, right? So 0.5 moles of nitrogen should be reacting with 1 mole of oxygen. Okay, so using that molar ratio, we know that our oxygen, we're going to use up 1 mole of it. So 4 minus 1 is going to leave us with 3 moles of oxygen. Okay, if we keep to the same color scheme, got 3 moles of oxygen left. Okay, so that's the equilibrium number of moles of oxygen. We're not quite finished yet because we also need to calculate the equilibrium number of moles of the product. Okay, so we need to this time round look at the molar ratio of reactants to product. So we know that, and perhaps let's use a different color this time. We're going to use pink. We know that the molar ratio of nitrogen to nitrogen dioxide is 1 to 2. Okay, so if you've got 1 mole of nitrogen reacting, you should expect to make 2 moles of nitrogen dioxide. So if we've got 0.5 moles of nitrogen reacting, we should expect to make 1 mole of nitrogen dioxide. Remember, a 1 to 2 ratio. So 0.5 moles of our nitrogen we should expect to make, or in other words, gain 1 mole of nitrogen dioxide. Okay, so if we highlight that so that we've got the right ratio, because you're using 0.5 moles of nitrogen, you would expect to form 1 mole of nitrogen dioxide, and so our equilibrium moles of nitrogen dioxide is 1.0. It's 1.0 because you had 0 of nitrogen dioxide at the start, you've made 1 mole of it, and so 1.0 plus 0 is of course 1.0. Okay, so that is hopefully a fairly straightforward example of calculating equilibrium moles. Now, the next thing I want us to look at are some similar examples, and then we'll look at the same exercise, but doing things algebraically, so to sharpen our thought processes when it comes to working out how much of something has reacted and how much of that thing will be left at equilibrium. Okay, so let's have a look at, okay, what I'm going to do at this point is stop and check that you haven't got any questions for me. Please bear with me 1 second while I do that. I'm going to stop sharing my screen, and I can bring up the chat box. Okay, so no, there are no questions at the minute, so I'll continue as we were. So back to my screen. Okay, good. So let's look at some more examples then of calculating equilibrium moles. So we're starting off with an initial set of conditions, so an initial number of moles, and then we're going to work out what the change in moles is, and therefore how many moles we've got at equilibrium. Okay, so let's look at the first example then. If I enlarge my screen, so it's a bit larger on your screen as well. Okay, so we're starting off with 1 mole of methane and 1 mole of water, and we don't have any carbon monoxide or hydrogen present at the start. Okay, it's also important that we pay attention to the balance equation and the stoichiometry, so the ratio of moles of the different reactants and products. Okay, so we're told that at equilibrium we've got 0.4 moles of carbon monoxide. Okay, now you can only form 0.4 moles of carbon monoxide if you've used up the same number of moles of methane or indeed water. How do we know this? Because the molar ratio of methane to carbon monoxide is 1 to 1. Okay, you can also choose to look at water to carbon monoxide. It's also 1 to 1. Okay, so If we don't have any carbon monoxide present at the start, and we've got 1 of methane and 1 of water, and we make 0.4 moles of carbon monoxide at equilibrium, it can only mean that we have used 0.4 moles of our methane. So the change in moles is minus 0.4, if I make that a bit smaller, minus 0.4 for our methane. Okay, so minus 0.4, which means that 1 minus 0.4 should be 0.6 moles. Okay, so that is a change in moles of our methane, leading to 0.6 moles at equilibrium. We can do the same exercise again. Molar ratio of water to carbon monoxide is 1 to 1. And so we're making 0.4 moles of carbon monoxide, we would have had to have used up 0.4 moles of water, and therefore at equilibrium you should expect to have 0.6 moles of water present. Okay, now how many moles of hydrogen are we going to have at equilibrium? We started off with 0 moles, and what are we going to have at equilibrium? So if you're using up 0.4 moles of methane or water, what is the molar ratio of methane or water to hydrogen? Okay, so if we consider methane, yellow this time, and hydrogen, we've got a molar ratio of 1 to 3. Okay, so we're using up 0.4 moles of methane. We would expect to make 0.4 times 3 moles of hydrogen. Okay, so we've got plus, well, I can do that and use a pen. So we've got plus 1.2 moles of our hydrogen. How did we get plus 1.2? By multiplying 0.4 by 3, which is the number of moles of methane used by the molar ratio 1 to 3. So 1 mole of methane giving you 3 moles of hydrogen. Okay, so that's the change in the number of moles, and therefore at equilibrium we would expect to have 1.2 moles of our hydrogen. Okay, and if we consider the change in moles of carbon monoxide, we sort of skipped over it because we'd already been given the number of moles at equilibrium. That would also be plus 0.4. Okay, so that's the first example, working out the equilibrium number of moles. I'm going to do one more example, and then we'll look at the same type of problem, but algebraically. So the next equation we want to look at is the formation of ammonia from nitrogen and hydrogen. So another equation or reaction that you're quite familiar with from the Haber process. And this time round, we're starting off with 0.1 moles of nitrogen and 0.1 moles of hydrogen. And at the beginning of the reaction, we've got no ammonia present at all. Okay, so just moles of reactants present. At equilibrium, we are told that you've got 0.07 moles of nitrogen left. Okay, so we've used up an amount of nitrogen and we've got 0.07 of it left. So we can work out the change in the number of moles. Okay, so nitrogen is being used up and the exact amount being used up is 0.03 to give us 0.07 left over. Okay, now if we're using up 0.03 moles of nitrogen in the reaction, how many moles of hydrogen are we going to be using up? Here you need to consider the number of moles of nitrogen to the number of moles of hydrogen. Okay, it's a ratio of 1 to 3. So if we used up 1 mole of nitrogen, we would expect that 3 moles of hydrogen would be used up. That means that if we use 0.03 moles of nitrogen, we would expect to use up 3 times that amount in hydrogen. So here we've got 0.09. Okay, so keeping to the molar ratio. Okay, so if we've used up 0.09 moles of hydrogen out of the 0.1 that we started with, what is the equilibrium moles of hydrogen? Of course, that would be 0.01. And then we can move on to looking at how many moles of ammonia you would expect to form at equilibrium. Okay, so to do that, you can pick, again, the molar ratio of nitrogen to ammonia. Okay, so this time round, the molar ratio in question is 1 to 2. 1 mole of nitrogen reacting to form 2 moles of ammonia. Now, we know that only 0.03 moles of nitrogen have reacted. So 0.03 moles of nitrogen have reacted. We're going to be forming 2 times that number of moles in ammonia. Okay, so we would expect to form 2 times 0.03, which would be 2 times 0.03, which would be equal to 0.06. Okay, so 0.06 moles of ammonia has been formed, and therefore the equilibrium moles is 0 plus 0.06, and that would be your equilibrium amount. Okay, so 0.03 moles of nitrogen reacts to leave you with 0.07 of nitrogen left, and that 0.03 moles of nitrogen will react with 3 times that amount, so 0.09 moles of hydrogen, leaving you with 0.01 moles of hydrogen left. Each mole of nitrogen forms 2 moles of ammonia, so 0.03 should form 0.06 moles of ammonia. Okay, so that's working out equilibrium quantities. Now, to work out values of Kc or Kp, we'd then go on to use these equilibrium moles that we've calculated to either work out the equilibrium concentrations or to work out the partial pressures for the gases more appropriately to allow you to work out Kp. But we'll get to that very shortly. Let's look at another type of problem, this time sort of looking at the equations we've just seen, or the reactions we've just seen, but in algebraic terms. So this time round, we're thinking in terms of x's, essentially. So a bit of algebra here, not very different to what we've been doing with actual numbers. So we're starting off with the same equation for making ammonia from nitrogen and hydrogen. So 1 mole of nitrogen reacting with 3 moles of hydrogen to give you 2 moles of ammonia. Okay, this time around we've got different starting quantities of nitrogen and hydrogen. So we've got 1 mole of nitrogen to start with and 3 moles of hydrogen to start with, and no moles of ammonia at all. Okay, at equilibrium, we've got 1 minus x moles of nitrogen left. Okay, so that is telling us that we've used up x moles of nitrogen. So minus x is your change in moles. We've used up, that minus sign is telling you that we've used up or lost x moles of nitrogen. Okay, so we also know that each mole of nitrogen reacts with 3 moles of hydrogen. So if x moles of nitrogen has reacted, we would expect that it would have reacted with 3x moles of hydrogen. Okay, so we would expect to have lost 3x of hydrogen, in other words, minus 3x. Okay, so how many moles of hydrogen have we got at equilibrium? Well, that has to be 3x taken away from the 3 moles we had at the start, so 3 minus 3x. Okay, so that's the equilibrium moles of hydrogen sorted out. Now, we need to do the same for ammonia. And at the start, we've got 0 moles of ammonia, but we know that x moles of nitrogen reacts. If x moles of nitrogen reacts, we need to consider the molar ratio of nitrogen to ammonia. And remember, it is 1 to 2, as given by your balanced equation. So, if x moles of nitrogen is reacting, we would expect to make 2x moles of ammonia. Okay, so we've got plus 2x moles of ammonia being made, and therefore at equilibrium we've got 0 plus 2x to give us 2x moles of ammonia. Okay, so the same exercise, but in more abstract terms, not using actual numbers. Let's do one more example. This time round at equilibrium, we're told how much ammonia we've got. Okay, so we've got 2x of ammonia made. Now, if we want to know what the change in moles of our nitrogen is, we need to go back and think about the ratio of nitrogen to ammonia. It's 1 to 2. So if we're making 2 moles of ammonia, we would have had to use 1 mole of nitrogen to make it. If we're making 2x moles of ammonia, we would have had to use up x moles of nitrogen. Okay, so in terms of the change in moles of nitrogen, minus x, or using up x moles of nitrogen. And that means that at equilibrium, you've got 2 minus x moles of nitrogen left. Now, if you're using up x moles of nitrogen, that x moles of nitrogen has to react with 3 moles of our hydrogen. Why? Because 1 mole of nitrogen reacts with 3 moles of hydrogen. Okay, so we would expect that you would use up 3x moles of hydrogen. Okay, so at equilibrium, we would therefore have 2 minus 3x of our hydrogen. Okay, so let's go through this again. We have 2 moles of nitrogen and 2 moles of hydrogen in our mixture at the start and no ammonia at all. Okay, so I'll highlight these for you. 2, 2, and 0. At equilibrium, we're told that 2x of ammonia has been formed. Okay, and so working backwards using the molar ratio of ammonia and nitrogen, we can deduce that if 1 mole of nitrogen forms 2 moles of ammonia, then you would need 1x of nitrogen to form the 2x of ammonia that we've got. Okay, so we're using up x moles of nitrogen. That means at equilibrium, you've got 2 minus x moles of your nitrogen. Okay, if x moles of nitrogen is being used up, the molar ratio of nitrogen to hydrogen is 1 to 3. That must mean that you're going to be using up 3x moles of hydrogen. Okay, so at equilibrium, you should have 2 minus the 3x moles shown here. Okay, so no doubt you can all go away and sort of complete the rest of the problems. And if you do come across any issues at all, please do get in touch with us. We're more than happy to write back to you with solutions to your problems. Okay, so let's apply what we've just been looking at to some actual exam questions. Let's see what sorts of questions we will be faced with in an actual OCR exam. Now, this one is taken from 2016 paper 1, AS paper, and we're looking at this particular reaction between sulfur dioxide and oxygen to give us sulfur trioxide. So this is one of the reactions involved in the contact process, the industrial manufacture of sulfuric acid. Okay, so I just want to highlight the equation, and the question I want us to actually focus on is the quantitative side, which is working out the equilibrium concentration of one of our species in this reaction using the value of Kc given to us. Okay, so in part B of question 25, we're told that under certain conditions, Kc for the equilibrium is 0.160 deciliters cubed per mole. Okay, now the equilibrium mixture under these conditions has the following concentrations of sulfur dioxide and oxygen. You've got 2 moles per deciliters cubed of sulfur dioxide, and you've got 1.2 moles per deciliters cubed of oxygen. We're asked to use the value of Kc, so using the value of Kc, if we can highlight that, explain whether the equilibrium position will be towards the right or towards the left under these conditions. Is it towards the right or towards the left? Okay, so we need to state in which direction the equilibrium will lie, and then say why. Okay, so the first thing we need to think about is the value of Kc. Now, Kc here is less than 1, because we've got a value of 0.16. Okay, so Kc is less than 1. That is telling me that the numerator for the equilibrium expression for Kc is smaller than the denominator. Okay, so that's telling me that you've got more you've got more reactants than you've got products. Okay, so in other words, the equilibrium lies to the left. Okay, so Kc is less than 1, therefore equilibrium position will be towards the left. In other words, more reactants than products. Okay, so we've been tested on our knowledge of the significance of the value, the numerical value of Kc here. Okay, so Kc less than 1 means that you've got mostly reactants. Kc greater than 1 means you've got mostly products. So we're looking at the ratio of reactants to products here. Okay, so the second part of the question asks us to calculate the concentration of SO3 in the equilibrium mixture. In order to do that, we need to go back to look at the equation and to then write our expression for Kc. Okay, so Kc is going to be equal to, you go one page back, it's going to be equal to the concentration of SO3 raised to the power 2 and divided by concentration of SO2 raised to the power 2 times the concentration of oxygen. Okay, so we need to start off with that expression first of all. And then we can rearrange it to make the square of SO3 concentration the subject. Okay, so what I'd do first of all is rearrange my equation, and that would be equal to Kc times the square of our SO2 concentration times our oxygen concentration. And then to finish things off, as far as getting an expression that allows you to work out the SO3 concentration, I'll take the square root of both sides so that I've got SO3 concentration being equal to the square root of Kc times SO2 concentration raised to the power 2 times O2 concentration. And then it just becomes a case of plugging in the numbers. Okay, so we want the square root of Kc, which we're told is 0.16, 0.160, times the square of SO2, which is 4, so 2 squared times 1.2. And if we do all of that, I'm going to very quickly punch all of that into my calculator. So I've got 0.16 times 4 times 1.2. Okay, and I'm going to take the square root of that answer, which gives me 0.876. So that's 3 significant figures, 0.876 moles per decimeter cubed. Okay, so that's a typical calculation for Kc calculation, except this time we weren't being asked to find Kc, but one of the concentration terms in our expression for Kc. Okay, let's have another look at another problem. Let's look at this one here. So this is another question, this time round from the 2017 paper. And if I, there we go. So this is a 2017 AS paper. And we're looking at a reaction between carbon monoxide and hydrogen to give us methanol. Okay, so in this problem, we've been given equilibrium concentrations for the different species, and we're asked to calculate the numerical value of Kc for this equilibrium. So if we highlight the main part of the task, that's what we're interested in, and we want to give our answer to an appropriate number of significant figures. Two things to bear in mind. So the chemist investigates the equilibrium that produces methanol. The chemist mixes CO and H2 and leaves the mixture to react until equilibrium is reached. The equilibrium mixture is analyzed and found to contain the following concentration. So let's start by writing an expression for Kc. Okay, so we go Kc is equal to the concentration of methanol, I keep saying ethanol, so methanol divided by the concentration for carbon monoxide times the concentration of hydrogen raised to the power 2. That is our expression. And then the next part of the problem is to plug in numbers for this calculation. Okay, so we've got, for our methanol, it's got me again, we've got 0.26 at equilibrium divided by carbon monoxide, which is 0.31, and we've got, for hydrogen, we've got 0.24 to the power 2. Okay, and if we plug in all of that into our calculator, I should very quickly do that. So we've got 0.24 square, and if we multiply that by 0.31, and then if we divide 0.26 by, we should get 14.6. So to 3 significant figures would be the appropriate number, so 14.6. And the answer is, of course, decimeter squared, mole to the -6. Okay, so if you're wondering about the units, and perhaps this would be a good opportunity to look at why the units are what they are. Sometimes you are asked to calculate the units. A handy way of working out the units is to write out the units of concentration for each term that you've got in your expression for Kc. So for the expression on the left, we've got the concentration of methanol, so mole and dm to the -3. So we've got methanol, and then underneath that, you've got mole dm to the -3 for carbon monoxide. And then for hydrogen, it's of course the square of the concentration. So you're going to have mole dm to the -3 times mole dm to the -3. So you're going to write it out twice. And then if you cancel out the terms at the top and at the bottom, you're left with 1 over mole dm to the -3 times mole dm to the -3. Of course, that works out as, if we dm to the -6 mole to the -2 dm to the -6. Okay, so the thing that might have got this wrong in the exam paper. So we've got dm to the power 2 mole to the -6 when it should be the other way around. It should be dm to the 6 and mole 2. So that should be mole to the power 2, dm2. Have we got this right? Yeah, dm to the minus 6 is at the bottom, so mole to the minus 2 should become, and dm to the 6. Okay. So that should be the correct unit. So the exam board have got the units wrong in this. So anyway, the numerical answer is 14.6, which is what we're after. Right, let's have one more go at another question. This time round, we've got, what have we got here? Okay, let's look at this one. It's another KC calculation. We're looking at nitrogen monoxide, 2 moles of nitrogen monoxide reacting with oxygen to give us 2 moles of nitrogen dioxide. Okay, so writing an expression for KC should be straightforward. Should be NO2 in square brackets, raised to the power 2. It's going to be divided by NO concentration raised to the power 2 times O2 concentration. And the units, if we write out the units, so mole per decimeters cubed times mole per decimeters cubed, and then do the same at the bottom. And another mole per decimeter cubed term. And then we can cancel things out. So that cancels out and that cancels out. And so we're left with 1 over mole per decimeter cubed. And so that would give us dm to the 3 mole to the minus 1. Okay, so that is our units shown there. And if we quickly move on to the calculation, we're told that the chemist mixes together nitrogen and oxygen and pressurizes the gases so that the total gas volume is 4 decimeters cubed. The mixture is allowed to reach equilibrium at constant temperature and volume. The equilibrium mixture contains the given number of moles of nitrogen monoxide, 0.4, and 0.8 moles of oxygen. And under these conditions, the numerical value of Kc is 45. Calculate the amount in moles of NO2 in the equilibrium mixture. Okay, so we want moles of NO2 in the equilibrium mixture. So what we can do is rearrange our expression for Kc to make moles of NO2 subject. So we're going to have NO2 square of NO2 concentration is equal to Kc times R NO raised to the power 2 and O2. Okay, and then we're going to have concentration of NO2 being given by the square root of Kc times NO2, sorry, NO I should say, NO to the power 2 and O2. Okay, so we're pretty much set to go. We can work out what the concentration is of NO2, and then we can use the volume to work out the number of moles. We don't need to do that. There we go. So if we go back and if we plug in all of our numbers, so Kc we're told is equal to 45. 45 times, we want the concentration of NO2, which we're given, sorry, not NO2, NO, which we're given as 0.4 divided by, so if we work out the NO concentration, 0.4 divided by 4, which is equal to 0.1. Okay, so the 10th, yeah, so that's 0.1 square. And oxygen would be, so we've got 0.8 moles of oxygen present in the same volume, so we would expect to have double the concentration of oxygen, so that would be 0.2. Okay, so we're pretty much set. Again, let's plug all of that into my calculator. So I've got 45 times 0.1 times 0.1 times 0.2 equal to 9 over 100. And if we find the square root of that, gives us 0.3. Okay, so 0.3 is our concentration. But we want we're asked to calculate the amount in moles, so we want the number of moles of NO2. So we know that concentration is equal to moles over volume in dm cubed. So simply put, our moles is equal to concentration, which is 0.3, times the volume in dm cubed, which is 4, and that gives us 1.2, I believe. Should be, let's double check that. So yep, so that gives us 1.2 moles as our answer. Okay, so hopefully you've got a sense of the sorts of calculations that you would be required to do. So working out equilibrium moles, working out equilibrium concentrations, and then going on to calculate either a value for Kc or going on to calculate a missing concentration term from the expression for Kc. It's a very similar sort of deal with KP calculations. Unfortunately, we haven't had the chance to go through any. There may well be one or two. Let's see if we can squeeze in one more calculation. Let's have a look at this one here. We don't get to do a KP calculation here, but we can very quickly look at what's going on here. So you've got an equation, again, showing the formation of nitrogen dioxide, and you've got the values for Kp at different temperatures. So we're looking at how temperature affects the value of Kp. Of course, temperature will change the numerical value of the equilibrium constant, unlike other conditions. So at low temperature, you've got a very high Kp, so lots of products versus reactants. And at higher temperature, you've got a very low Kp, so more reactants than products. So increasing the temperature causes a shift of equilibrium to the left. Decreasing the temperature pushes the equilibrium to the right. Okay, so predict with a reason whether the forward reaction is exothermic. So forward reaction, when is a forward reaction favored? The forward reaction is favored when you lower the temperature. So if you lower the temperature, the Chateau's principle says the equilibrium will act to oppose this by increasing the temperature. The forward reaction must be exothermic. So that increases the temperature back up again. Okay, right, so the chemist increases the pressure of the equilibrium mixture at the same temperature. State and explain in terms of Kp how you would expect the equilibrium position to change. Okay, so you would expect, so in this equilibrium, you've got more moles of gas on the left than you've got on the right. Okay, so if we increase the pressure, shifts equilibrium to the right hand side, as you've got fewer moles. Why does that happen in terms of Kp? So if you increase the pressure, the contribution of the partial pressures of the reactants goes up a lot more. So increased pressure means partial pressure increases a lot more. Therefore, reactants are used up. Make more products. increasing partial pressure and restoring Kp to its original value. Okay, so what's going on is as soon as you change the pressure, you no longer have an equilibrium. So you've got your reactants, because there are more moles of reactants, you've got their contribution to the total pressure being a lot greater than the contribution of your products. As a result, your reactants get used up to form more products, and you've got your partial pressures of your products increasing to restore Kp back to its original value. Okay, so Kp does not change when pressure is increased, or indeed when pressure is decreased. Okay, so hopefully you found this session useful. I would highly recommend that you tackle the rest of the questions we've not been able to go through. If you have any questions at all, please do drop us a line at boostrevision.com and we will write back to you in a timely fashion. Otherwise, it's been a pleasure looking at Kp and Kc calculations with you, and I look forward to you joining me again soon. Thank you very much and have a great weekend.